Okay, first of all, welcome everyone, and thank you for staying through the afternoon, even though I can understand the weather and the beaches are very tempting. My name is Timur Kuzu. I'm a PhD student from RWTH Aachen University in Germany, and today I will present our work on an evaluation of mobile platforms for the automation of metro tunnel inspections. So to start, let's look at some numbers on why metro tunnels are particularly interesting, especially from like a sociological perspective. So we can see that in the past 75 years, from 1950 to 2025, the urban population has moved from the urban population has moved from 20% of the global population to 45%. And in a similar period of time, from 1950 to 2015, we can see that the cumulative global length of metro tunnel systems has increased more than tenfold, from 1,250 kilometers to over 13,000 kilometers in 2015. And as part of that, we can observe that metro tunnels have become a crucial part of urban transportation, resulting in an annual ridership count of 58 billion in 2023, accounting for up to 33% of the modal share in major cities such as Tokyo. Now, the second aspect is related to the maintenance of the tunnel. We already established that there is a substantial amount of metro tunnel systems available, and now they need to somehow be kept operational. And as everyone here can imagine, due to material aging, heavy loads, and general environmental conditions, these infrastructure buildings are prone to building damages, which are required to be inspected and potentially maintained. So I don't know if anyone has ever been inside a metro tunnel and had the opportunity to assess the conditions of them, but at least for German metro tunnels, since a lot of them were built after either the First or Second World War, they're often in, let's say, improvable conditions. So what you will find often is damages in the form of cracks, leakages, cross-section deformations, and thus regular inspections are required to assess the building conditions, plan investments, and allocate repair as well as maintenance resources. Now, third, we have operational constraints that are unique to metro tunnel environments, such as timely limited inspection windows, which are during the nightly shutdowns of metro systems, metro-specific ground conditions, including the tracks, ballast, and cross tiles, which are on the surface of the metro tunnels, and these create fundamentally different conditions compared to, for example, road tunnels. So concluding the aspects I just mentioned, the paper focuses on the question of how do mobile platforms need to be designed to meet the demands of metro tunnel inspections. And to answer that, we are going to look at three different subtasks. The first one being a presentation of relevant mobile platform types for tunnel inspection tasks. And afterwards, we will look at the specific constraints that metro tunnel environments impose to automated inspection systems, meaning how do inspections of metro tunnels differ from inspections of road tunnels, for example. And lastly, we will evaluate the mobile platforms against these constraints by looking at functional and physical capabilities of the platforms to assess how suited they are for metro tunnels. Now, before we do so, let's also take a look at the methods we use to gather our information. So we used a mixed method approach, including a literature review to identify existing mobile inspection systems that have already been developed for road tunnels, railway tunnels, and metro systems, and extract key technical parameters such as payload capacity or runtime. And then we selected publications based on the maturity of the described systems with the goal of identifying relevant mobile platforms for automated inspections as well as their key system parameters. Then we conducted semi-structured interviews with metro tunnel operating agencies whose participants had a broad range of tasks from planning and scheduling to practicing on-site inspections themselves, and more organizational topics such as asset management. And the main goal was to establish existing maintenance procedures and conditions that are currently used in practice, as well as to gather insights into operational constraints that are not represented in literature otherwise. In total, we interviewed 6 members of German metro tunnel operating agencies, following an interview guideline on organizational processes of metro tunnel inspections, current maintenance strategies, handling of inspection data and reports, as well as operational constraints within the inspection process. Then lastly, we got our hands dirty and and did some in-person observations inside German metro tunnels during regular inspection and maintenance windows. And these focus on the physical environment and infrastructural conditions inside the tunnels, which are documented through photos and videos with the goal of identifying requirements that would otherwise either be not represented or underrepresented in literature. Now let's take a look at the results. So starting with the inspection platforms that we identified, they can generally be classified into 4 different categories. So the first category of inspection systems is, or can be classified as rail-bound vehicles, meaning they're inspection platforms that, as the name suggests, are using the tracks of the metro tunnel for transportation. And the second type of systems will be summarized as wheeled and tracked robots. So any type of platform that uses either wheels or tracks is going to be associated within that category. And they usually offer good performance in payload capacity, meaning that large sensor setups can be integrated with relatively simple motion control of the systems, but they generally lack movement flexibility. And third, we have quadruped robots that mimic the motion capabilities and approaches of 4-legged animals such as dogs, which will allow them to be more flexible with their movements at the cost of less hardware payload and higher integration effort due to the complex joint systems. And lastly, we have inspection systems mounted on UAVs, meaning they are able to fly through the tunnel and can thus operate independent of what the surface conditions on the ground are going to look like. Now, after establishing the main inspection platforms, we want to take a look at the specific operating constraints that we have for metro tunnel inspections, since they will usually largely differ from the conditions that we have, for example, in road tunnels. Now, the constraints are separated into 3 different domains, depending on the information source that we use to acquire a specific constraint. And starting with the literature-based constraints, we first have the fact that within metro tunnels, we operate in a GNSS-denied environment, meaning we can't rely on satellites to localize ourselves during automated inspections. Next, we have 2 aspects that go into similar direction regarding the physical conditions inside the metro tunnel, which is low illumination, since the trains usually don't need any light to operate, as well as high dust pollution, largely due to the braking of the trains, which again make navigation and localization more challenging. And looking at the interview-based constraints, one aspect is that very different from other infrastructure buildings, we have limited inspection windows, which is, depending on the metro system, usually around 3 hours per day during nightly shutdowns. And what we were also told is that during these timeframes, there is maintenance work that is being done on the tracks. For example, if there is a damaged fastener that holds the tracks onto the cross ties, and if they need to be maintained, then the rails are not available during that period of time. And when doing the observations, we could identify 2 more aspects related to physical environment, one being just the geometry of the railway track itself and the obstacles that we have between the tracks, as well as a limited tunnel access that often requires stairs or similar to get into the tunnel from the metro stations. Now, after looking at the platforms themselves and the operating constraints we have for metro tunnel inspections, this table shows our 4 platforms on the horizontal axis, as well as key characteristics of the hardware platforms on the vertical axis. Now, due to the time, we won't go over every single one of the aspects, but looking at a few of them, for example, the payload capacity, we can see that rail-bound, wheeled, and tracked systems generally offer high payload, meaning they're able to incorporate more complex sensor setups and that can be carried, while quadruped and especially UAVs are more limited in their weight capacity. And looking at the system runtime, we can see that since inspection window is usually limited to around 3 hours, there's no real benefit of having systems that largely exceed the time period. And then we also have some general considerations, for example, that the rail-bound systems are dependent on the availability of tracks, and that the quadruped robots, for example, can have stair walking capabilities, meaning you will be able to get down to the metro tunnel from the stations. Now, based on the operating constraints and physical platform characteristics that we just mentioned, each platform excels in specific aspects, which is why scenario-specific deployment strategies rather than generic platform recommendations are proposed. And yeah, for the rail-bound, we can see that there is that they generally excel in linear inspections with high payload capacity for comprehensive sensor setups, and they perform very well in long straight sections with uninterrupted track access. And for wheeled and tracked robots, they have generally balanced physical capabilities, yeah, being efficient on flat and continuous areas, yeah, which are sometimes on the size of the tunnel tracks, and yeah, they have limited obstacle and track avoidance, and yeah, so they're best used in simple and flat sections without many obstacles. And the quadruped robots offer high flexibility due to the versatile locomotion, yeah, incorporating stair climbing activities for uneven terrain, and yeah, they suffer from high control complexity and risk of instability when slipping, for example. And the UAVs offer fast deployment. They're independent to the ground and can access areas which are otherwise inaccessible. For example, if there is a ceiling that is blocked by an obstacle. And yeah, they generally have short runtime and low payload and can incorporate less comprehensive sensor setups. So lastly, for an outlook, so how should this encourage further research? So we saw that each system has its own use cases and benefits, but of course you can also start to combine multiple platforms to compensate for the benefits and drawbacks of single approaches, thus enabling hybrid platform inspections. So while there have been proposed similar systems, such as the combination of a quadruped robot that carries a drone shown in the image, they are often conceptual with a lower level of system maturity, and there is no incorporation yet on the specific requirements that we can see in metro tunnels that we just mentioned. And yeah, if you're interested in the topic, then feel free to come up to me or connect on LinkedIn, and thank you for listening.